Hello friends, welcome to our channel Piping Mantra. In this video, we are going to discuss about P&IDs, as in how to read a P&ID, different symbols used in all the information we can get through a P&ID, and what are the different considerations we have to take while developing the P&ID and obviously its uses. So let's start. The types of drawings there are process flow diagrams, that is PFD, which shows what a process does. Next comes piping and instrument drawings called P&IDs, which is our main topic, and it shows how a process works. Next come layout drawings. It shows how the process looks. Next comes mechanical drawings and construction drawings. These are basically shows how to build the plant. Now the question arises, what is a P&ID? A piping and instrumentation diagram, that is PID, is a graphic representation of a process system that includes the piping, vessels, control valves, instrumentation, equipment, and other process components in the system. The P&ID is the primary schematic drawing used for laying out a process control system's installation, based on process flow diagram, which indicates the more general flow of plant processes and the relationship between major equipment of a plant facility. Now, let's start with what are symbols and different types of symbols used in P&IDs. A standard set of diagrams which shows the interconnection of process equipment and the instrumentation used to control the process. The instrumentation symbols used in these drawings are generally based on International Society of Automation standard ANSI/ISA S5.1, ISO 14617-6 and ISO 10628. The symbols used to represent process equipment items are frequently the same as described for the process flow diagrams. These symbols are also labeled with words, letters, and the numbers to further identify and specify the components that they are representing. The more pictorial style will promote greater familiarity with the equipment, and the designer's objective of providing maximum information at minimum cost will be achieved. It is important to note that these symbols are not to scale and are not dimensionally accurate. Another important consideration is that the diagrams do not always represent the physical locations and proximity of each component. Some of the standard symbols used in the P&IDs are shown in the figure. The process lines are the lines where the process media actually flows through. They are represented by different types of lines, as you can see on your screen, like normal pipe, thermally insulated pipe, jacketed pipe, cooled or heated pipe, and flexible pipe. On a P&ID, each line will be labeled with a line number. For example, 3 inches -NL-121007-A11A-1H30. Now each of these components or parts have their own significance in the line number. Like 3 inch denotes the line size, which is mandatory. NL represents the fluid service. Next is 121007. Here 12 signifies the unit facility number, while 1007 denotes the serial number. This is mandatory. Now A11A represents the pipe service class. It is also mandatory, but again it depends on project to project. In A11A, A denotes the flange rating like 150 pound or 300 pound. 11 denote the piping material, and A is the suffix qualifying the piping material. IH is the hot insulation, and 30 denotes the insulation thickness. There are different types of insulations present and include IC cold insulation, safety insulation IS, acoustic or sound insulation IA, personal protection PP. There are different types of tracings, which include electrical tracing ET, steam tracing ST, chill water tracing CWT, thermal or hot oil tracing TT. Now different companies or projects use different structures for these numbers, but they all contain almost the same information. Now there are two methods to illustrate when pipes cross on drawings but are not physically connected. These two methods are shown on your screens right now. Either use a small hump to show one going over the other, or break one of the lines very near the other to show it going under it. Line break. We come across it more frequently while reading a P&Id than any other thing. Now, what is a line break? There is a symbol we use to represent the line break. This can be shown in three ways as shown on your screen. There is this detail where if we show the triangle, that means there is a line break, and if this symbol is shown without the small triangle, that means there is some property change, like either insulation or tracing or anything else. But if this triangle is shown on the P&Id, then it definitely means that there is a line number change. Both the changed line numbers will be shown as well. Process lines are bolder than other lines, such as those that represent electric, pneumatic, or data signals. Process control systems use various types of signals to communicate information between components, instruments, and the control system computers. Each type of signal has its own line type to explicitly identify the type of signal that travels along it. Like pneumatic signals, guided electromagnetic sonic or fiber optic signals, electronic or electric signals, unguided electromagnetic sonic or wireless signal, hydraulic signal, various data communication signals. This is how we show a valve connected to a pipe. This is a typical two-way valve. Likewise, there are typically three-way, four-way valves are connected as shown on your screens. These are different valve symbols. Valve representation symbols vary project to project, so it is always advisable to refer the legend sheet right before starting to work on P&IDs for better understanding. The basic fundamental representation of the valves are shown on your screens right now. Now, valve actuators are usually shown like this. We have different valve actuators like manually operated, pneumatic actuators rotary piston type, electrical actuators, and hydraulic actuators. Now, valve connection types. However, this is optional. In any case, we have to use project specific piping material specification for end connection of valve. But typically we use such representations to show different end connections like flanged, threaded, welded, socket welded. Often we see some alphabets or abbreviations are written along with these valves like NO, NC, FO, FC, which stands for normally open, normally close, fail open, fail close respectively. Fail open or fail close valves would open or close at a loss of signal or power. These type of valve required air pressure to stay open or close. CSO CSC, car seal open and car seal close. Simple device is used to lock or seal the valve in open and close position to prevent unauthorized operation of valve. Now let's see some graphical representation used to refer various equipments like pumps and compressors. You can see on your screens various pumps and compressors, tanks, vessels, and drums. The picture on your screen shows different types of tank, vessels, and drums. Refer this picture for different type of heat exchangers, air coolers, heaters, etc. The next picture shows the graphical representation of almost all other piping components used to provide adequate information of the concerned line without having to refer a lot of individual documents. Please keep in mind that these are general symbols and these may vary from project to project in reality. Now let's talk about instruments. As we already discussed previously, various instrument signals are shown as follows. Instrumentation refers to devices that sense, measure, indicate, transmit, and/or record physical properties within a system. For these type of components, there is a slightly different approach. The components are represented by what is called a bubble. The bubble is a simple circle, square, or hexagonal shape. The different types with their meanings are as shown. A bubble with no line means that the device and or its display are physically located in the field, and if it has a display, it is only readable locally. A solid line in the bubble means that the display is located on a main control panel or video display and is normally accessible to the operator. A dashed line in a circle means that the display is not normally accessible to the operator. A double solid line in the circle means that the display is located on a secondary or local control panel that is normally accessible to the operator. A double dashed line means that the display is located in a secondary control panel and is not normally accessible to the operator. Square bubble represent shared display. A shared device either displays information from multiple instruments, control multiple instruments, or both. Inside the square will be either a circle or a diamond. A circle represents that it is the primary choice or basic process control system. A diamond represents that it is the alternate choice or safety instrumented system. Hexagonal bubbles represent computer systems. Circular bubbles represent discrete instruments. This type of bubble is also used to define the function of final control elements, such as valves. This is done with a call-out line pointing to the symbol for the control element. The letters and numbers inside the bubble are described as tag numbers. Inside the shape, there are letters and numbers used to designate the property being measured, such as flow rate, pressure, temperature, or level, and the function performed with that measurement. Typical functions are display, record, transmit, and control. For example, P is for pressure, T is for temperature, F is for flow, and L is for level. And all the other indicators, controllers, switch, element, transmit, gauge, and valve are typically the functions they can perform. The instruments are identified up to 5 letters. 2 are a minimum. First letter is the property being measured, like flow rate, pressure, temperature, and level. Second letter is a modifier, like D is for differential and F is for ratio. Third letter indicates the passive or readout function, like A is for alarm, R is for record, I is for indicator, and G is for gauge. Fourth letter is for active or output function, like C is for controller, T is for transmit, S is for switch, V is for valve. Fifth is the function modifier, like H is for high, L is for low, O is for open, C is for closed. We can simply omit these if no modifiers apply. The first P&ID in the project should contain a legend defining all symbols used. If certain symbols are defined elsewhere, it may be appropriate to only refer their source. Let's see an example of a P&ID. The P&ID should show process pipe and its line number and size as we discussed early in the video. All the mechanical equipments to be shown in P&ID, like here pump is shown with its unique tag number. All nozzles on equipment items must be shown on a roughly accurate location, whether for piping connections, instruments, vents, drains, or spares. All the nozzles must be given the tag numbers. The pipework representation is non-scalar and entirely symbolic at this stage. Piping specifications to be used for each pipe and the junction points where two specifications join. We use breaks where we have two different materials, tracing or insulation in connect. It is shown like this. All the different type of valves which is going to be used in plant to be shown in P&ID, like check and gate valve symbols, is used here. Piping fittings such as elbows, flanges, etc. are not shown, but reducers with their sizes should always be shown. Direction of flow should be marked properly in each line. Process drains and vents are to be shown on P&IDs, whereas we do not need to show hydrotest drains and vents. All inline fittings such as side classes, strainers, steam traps, etc. are to be shown. All special items are to be shown with proper symbol, like here as we have shown flow element with its accessories. P&ID should show against each pipe its start and finish terminal points in the direction of process flow. The location of ancillary equipment for every in-pipe instrument like relief valve is shown here. You can also see a control valve and a three-way safety valve with proper signal and interlock is shown here. Let's see other minute details like tracing insulation, slope and applicable notes. The P&ID contains a minimum amount of text in the form of notes. The system descriptions minimizes the need for text on the P&ID. Last but not the least, you should use project defined template which should specify description of P&ID specific to stream or unit along with project name and client name. All the valves and functional fittings required in each pipe to meet all the above foreseeable conditions must be shown and identified in their correct functional location. For example, a control valve must have block valves upstream and downstream. It is no use showing both block valves on one side and hoping that the detailed piping designer will realize what is needed. In short, everything needed on plant must be shown in the P&ID and accounted for purchasing and erection stages. Sequencing on object is a very important aspect of P&ID. Conversely, any item not shown in the P&ID will not be installed on the plant. Now let's discuss about different phases of P&ID. It is grouped by specific sections of the process. P&IDs are originally drawn up at the design stage from a combination of process flow sheet data, the mechanical process equipment design, and the instrumentation engineering design. Parallel to the initial P&ID work, the pipe sizes should be calculated. The process engineer for the main process lines will normally prepare a very rough size estimate. But with the final layout available and all pipes shown diagrammatically in the P&ID, the process designer can assign pipe sizes regarded as finalized except for the final check at final detail stage, that is hydraulics. The process designer should remember that the P&ID covers all stages of plant startup, operation and emergency, and must ensure that the pipe sizes selected cover all these conditions adequately. At this stage, the process engineer must consider the terminal point for all the pipes shown in the P&ID so that each individual pipe can be given a unique identity known as the line number. In a very simple case, a pipe runs from one equipment item to another with two terminal points without a branch connection. This simple case presents no difficulties, but in the majority of cases found in practice, common problems arises in case of following. Pipe changes specification between equipment items. Pipe branches to feed more than one item. For example, when a pair of pumps feed one vessel, branch pipes are often connected to other pipes. For example, utility subheaders feeding several items or a process pipe with a branch to another process pipe to meet a startup condition. Equipment items are bypassed. Control valves in pipes have a bypass loop fitted. In establishing how many pipes exist, some general principles can be stated to distinguish between pipes with more than two terminal points and cases where lines must be split into two or more pipes. A pipe must have only one specification to ensure that only one type of material is used for fabrication. Hence, if the specification changes, a new pipe must be created at the specification change point. Pipes can have more than 2 terminals but should run from on plant location to one other location. Those which connect to 2 items such as a pair of pumps or heat exchangers can properly be regarded as one pipe, but a branch run to a separate vessel removed from the main run of the pipe should be treated as a separate pipe and identified as such. When a small piece of equipment is bypassed, the inlet pipe can be treated as a pipe with 2 terminals at the equipment location, one terminal connected to the equipment item and the other connected to the block valve. Similarly, the outlet pipe starts with 2 terminals at the outlet and the block valve. On larger equipment items where the bypass line may be around 20 feet or more, it is better to treat the bypass as a separate pipe. Bypass loops around control valves or similar equipment in a pipe should be treated as part of the pipe. So far, each pipe has been assigned terminal points, a specification and a size, but no identity. It is vital that every pipe can be identified by its own unique reference, and this can most easily be done by an alphanumeric system designed firstly to split the pipes by function and secondly to give each pipe in the function groups a number. The combination of function or number is unique and identified any pipe from all others. This we already discussed in the earlier part of the video. Strict control of modification procedure is essential to maintain control of all piping work. Virtually all the process know-how and much engineering technique are recorded on the P&ID and its security controlled to prevent information leakage to unauthorized persons. Now let's discuss about some of the applications of P&ID. The P&ID is the most important document produced by the process department working in close contact with the project, process and piping engineers. When complete, it will be used as a common data source by all the disciplines like piping, instrument, erection, and operating staff who require a clear, unambiguous statement of the piping design and connections. For design and layout of process system mainly by piping and instrument discipline are component specifications, development of control system schemes. P&IDs also are used as the basis for the live graphic representation of a process system in its HMI, that is human machine interface, or other control system. Safety and operational analysis (HAZOP), that is hazard and operability study. During the design stage, the diagram also provides the basis for the development of system control schemes, allowing for further safety and operational investigations, such as a hazard and operability study (HAZOP). To do this, it is critical to demonstrate the physical sequence of equipment and systems, as well as how these systems connect. Installation and/or build-out of the system. The P&ID provides direct input to the field for the physical design and installation of field-run piping. The P&IDs are also used by the startup organization for preparing, flushing, testing, and blowout procedures for the piping system and by the plant operators to operate the system. The correctness and completeness of the P&ID drawings are crucial to the success of the startup program. Employee trainings of process system operation. Maintenance and modification to the system. P&IDs are also play a significant role in the maintenance and modification of the process after initial build. Modifications are red-penned onto the diagrams and are vital records of the current plant design. And there are many more applications of P&ID. Now, there are some various softwares which are to be used for P&ID development like AutoCAD, MicroStation, SmartPlant PID, Cadison, Visio P&ID, LucidChart PID, SolidPlant PID, ProCAD PID, etc. etc. So that is it guys. This is all for this video. Please do like, share and comment. If you have any queries on this topic or any other topic, please drop your query in the comments section below. I hope you like this. Stay tuned for the next video. Thank you.